Form 7 Physics for the momentum. Today we will be learning about the impulse equation, and there is a core practical to be learned about force exerted on an object and how it changes its momentum. And we will be learning about how to apply conservation of linear momentum problems in 2 dimensions, where earlier we learned one-dimensional problems in AS studies. Then we will be discussing about another practical about how to use ICT to analyze the collision between small spheres. And next we will try to understand how to determine whether a collision is elastic or inelastic. And finally, we will try to make the concept of momentum and concept of energy to combine with each other. Okay. So first of all, to proceed with, we will have a small revision about the 2 equations of momentum, which is momentum equals mass into velocity. Mass is measured in kilograms, velocity is measured in meters per second. Then we can have the unit Newton seconds. Then kinetic energy equation, the general equation for kinetic energy is half mv squared, where mass is measured in kilograms, speed is measured in meters per second, so the unit would become joules. Right. Now the impulse equation. Impulse is actually the force acting on a given time on an object. We know that when a force is acted upon an object for a long time, then there is a greater impulse, or even a greater force acting in a small time. It doesn't matter. If the force is very high, that is also giving us a very high impulse. However, if you can remember the equation force by the definition of Newton's second law, now it says that rate of change in momentum is directly proportional to the resultant force. Okay, so it tells us that resultant force is equal to rate of change in momentum, which means resultant force is equal to change in momentum divided by time taken. So change in momentum will be equal to force multiplied by time taken, which is indirectly the impulse. So we can tell impulse in 2 ways. That is, it can be either the force multiplied by time, or it can be either the change in momentum. This relationship comes with Newton's second law. Okay, now we'll look at a small example of how we can apply this theory. Okay, so it says that there is a body of mass 2 kg, which is initially at rest on a horizontal plane, and the force is also horizontal, 4.5 newtons, and it is acting only for 6 seconds. And find the magnitude of the impulse given to the body by the force. Okay, now before looking at the answer, we'll think mass is given and force is also given and the time is also given. Impulse equation. Okay, I can't go for momentum because velocity is not given, but I can go for the force into time equation because force and time both are given. So I will go to the previously learned impulse equals force into the acting time. So force multiplied by time, which gives us 27 Newton seconds. That is how we generally think of a question and write the answer. Right. So as I said earlier, now we will be looking at an investigation. How the relationship between force exerted on an object and its change of momentum. Right. So these are the steps. First of all, we add a known mass on the mass hanger. Then force acting on the trolley will be equal to mass on the mass hanger multiplied by 9.81, which means weight on the mass hanger. Then we release the trolley and we observe the final velocity after a known constant time. This can be done by the motion sensor. That's why we say observe, otherwise we could have told calculate. Right. Then we repeat the same above for different masses on the mass hanger. We can find the change in momentum, which is equal to final momentum minus initial momentum. But the thing is, initially it was at rest, so speed is 0. So change in momentum is equal to final momentum, which is mass into final velocity, which we observed earlier. Right, then we can plot a graph of force against momentum. If it is a straight line passing through the origin, then it tells us that force is directly proportional to the rate of change in momentum. Why I use the word rate is because we kept the experiment for a constant time. So force against momentum, if I divide momentum divided by this constant time also, it would be a similar graph. It's also a straight line passing through the origin. So we can say that Newton's second law is applied on this motion. We can go for another graph from this experiment. That is, we can plot a graph of impulse against final velocity. Now if you can remember, the equation impulse is equal to change in momentum. Or in other words, as the final momentum is there but initial momentum is 0, impulse is equal to mass into final velocity. Impulse equals mass into final velocity. So it is in the form of y equal mx graph. Impulse y equals m, gradient is the mass and x is the velocity. So it should be a straight line passing through the origin, where gradient will give us the mass of the system. That is the idea. Okay. Now we will look at a momentum in 2 dimensions. This is about a blue car and a red car colliding. Now if we see this figure, we can understand that this initial vehicle moves with a velocity of 20 meters per second, and the red one also, it is moving with 10 meters per second. These towards east and these towards north. Then after colliding, both of them moves in a different direction to their initial direction of motion. So when it comes to these kinds of momentum questions, we resolute the momentum, that is by resoluting the velocity vector, and we can use the principle of conservation of momentum, where it says that total momenta before a collision equal total momenta after a collision. Then we will select a particular direction and we will apply the conservation of momentum. So initially we will think that we will try to use the conservation of momentum towards right. If it is so, this blue car, we can consider that it has an initial momentum of 1000 multiplied by 20 towards right. But red car is not moving towards right, so its initial momentum towards right is 0. So initial momentum towards right is 20,000. Now we will think after the collision, both red and blue cars collides with each other and moves towards right, northeast direction. Mass of both of them will be 2000, and both of them would have a velocity of 11.2 meters per second. So 2000 multiplied by 11.2, if we take it in that way, it would be a bit of a problem. We should not take it in that way. We should take 2000 multiplied by 11.2, then the angle that they have given is 27 degrees north of east. So we have to resolute it downwards. Then it would be 2000 into 11.2 cos 27. It will give us the same answer as earlier. Okay, now we will move on to the next part, another small example. It is about an alpha particle interacting with a stationary nitrogen. Now earlier with the interaction I was just talking to you about how to apply conservation. Now I will tell you graphically, diagrammically, how to conserve momentum and how to resolute momentum. Now following diagram shows an alpha particle interacting with a stationary nitrogen nucleus. That means the alpha particle is coming. Here the stationary nitrogen nucleus is there. After collision, nitrogen nucleus travels in this way and alpha particle travels in this way. That is the idea. Finally, we have to calculate the speed of nitrogen particle, this one, after the collision. Okay. So, as I took earlier, in this answer also, I will take the horizontal direction. Now, alpha particle, initially it had a mass, alpha particle, of course, it has a mass of 4u and it has a velocity of 1.2 into 10 to the power 7 meters per second. Now we will think of the final, that means after the collision what would happen. In this diagram I am not going to draw anything in the angled directions. I am going to resolute them and write. So alpha particle was having a velocity of 6.93 into 10 to the power 6 in this direction. So I will resolute it away from 30 degrees. So it would be having a momentum upward, which is equal to 4u into 6.93 into 10 to the power 6. As we are moving away from 30 degrees, we write sine 30. It would give us this answer. And what about the horizontal direction? It would be 4u 6.93 into 10 to the power 6 cos 30. Then we will think of nitrogen. Nitrogen 1 would have a downward momentum of 14u into we don't know, sine 10.9, and horizontal rightward momentum of 14u into v cos 10.9. But I thought of taking the total momentum in the vertical direction. Why? It is because alpha particle was not moving vertically up. So initial momentum of alpha particle is 0. Then when we look at this diagram after the collision, alpha particle has a component of momentum towards up, so it's positive. But nitrogen has a component of its momentum downwards, so it's negative. Upward anything momentum positive, downward any momentum would be negative. So then the answer would be 1.39u into 10 to the power 7 minus 14u into v sine 10.9. That is the total vertical upward momentum after the collision. Theoretically we know that initial total momentum vertically upward should equal to final total momentum vertically upward. We will equate them and we will get the answer for V. A simple mathematical calculation thereafter. Okay, now as I said so earlier, there is a small experiment we have to do. It's using ICT to analyze the collision between small spheres. We keep a small camera fixed firmly to record frame by frame, and we keep a small sphere here and we release this sphere gently. Then we calculate the velocity of the ball bearing using the time per frame, which is taken from this camera, and the distance travelled within each frame. Then after the collision also we calculate the velocities of the two separate balls, and we measure the masses of each ball using a balance. Then we calculate the initial and final total momentum. If they are the same, experiment is successful. Right. Now we talked about momentum. Now it's time to go to energy. Now when we talk about energy in this lesson, it is going behind a word called elastic collision and inelastic collision. How? If the total energy is conserved, that is energy total before is equal to total energy after, we call that kind of a collision is an elastic collision. If during the collision kinetic energy before is greater than kinetic energy after, that type of a collision we call inelastic collision. But however, many students do some miscalculation when it comes to these questions. That is, they try to resolute energies. Remember, energy is not a vector, it is a scalar. So we should not resolute energies. Okay. Now I'm taking both the conservation of momentum and both the conservation of energy later. Here we will think of the conservation of energy. Now, even though they are moving at an angle, did I ever try to take the resolutions? No, you don't see any sine or cos, right? So we just take mass into velocity squared and divide by 2. So this is the initial kinetic energy, m1 u1 squared over 2. Final kinetic energy, this one is not having any kinetic energy. Final kinetic energy, m2 v2 squared over 2, m1 v1 squared over 2. We add them. If the final kinetic energy is equal to initial kinetic energy, it's an elastic collision. If the kinetic energy after is lesser than the initial kinetic energy, it's an inelastic collision. Okay. A small question about energies. Now we have shown that these values satisfies the condition for conservation of momentum in initial direction of ball 1, which is towards left. And finally we have shown that these values satisfy the condition for elastic collision. Okay. Momentum before 0.048. How do we calculate it? Mass into velocity, and it would give us 0.048. Momentum after, how do we calculate? Mass into velocity's component in the initial direction of ball 1 towards left. So that would be 0.066 into 0.63 cos 29. You see that I have resoluted towards 29, that's why I said cos 29. This one 0.35 cos 61. See, 0.35 cos 61. So we calculated them separately. You can see nicely momentum before equals momentum after, which means that it satisfies the principle of conservation of momentum. Now I'll ask you a small question. What if these two differ? Then the only answer that we can tell is there is an external unbalanced force acting on the system, therefore conservation of momentum is not valid. Okay. Now about the kinetic energy. I told you earlier that I am going to do a question about both momentum and kinetic energy. This is that question. So when we look at this one, we see that kinetic energy before half mv squared. Did I resolute? No, it is a scalar. It is equal to 0.0171 joules. Kinetic energy after, I calculated the kinetic energies of individual poles and I added them. Did I resolute? No, that is because they are scalars. So I see nicely that 0.0171 joules is equal to 0.0171 joules after collision. So we say total kinetic energy before equals total kinetic energy after, so kinetic energy is conserved. Right. Another small example. Show that momentum and kinetic energy are related by the equation Ek equal p squared over 2m. Ek is equal to mv squared over 2. But we can square this mass by multiplying the numerator by m and denominator by n. So it becomes m squared v squared over 2m. But we know that momentum is equal to mv, so momentum squared is equal to m squared v squared, which is this one. So I can replace this by momentum squared divided by 2m. We proved. Right. Hence determine the momentum of a proton with kinetic energy 18.8 kilo electron volts. Okay, so we'll see this one. Now we know that they have given us the momentum. Sorry, they are asking the momentum. They have given us the kinetic energy. But they did a tricky thing. They have not given us the kinetic energy in joules. So first of all, we will convert electron volts to joules. Then what we will do is, as they are asking the momentum, not the velocity, we will directly use p squared over 2m. Mass of the proton will be given in the formula sheet, so nothing to worry about that one. We found the kinetic energy in joules, p squared over 2m, then p would be equal to 3.17 into 10 to the power minus 21. Okay, now we were discussing almost everything about momentum and energy. So you can try questions in page number 12 and 13 in your physics book. If you have any doubt, you can always contact. Thank you.